أعوذ بالله من الشيطان الرجيم. Bismillahirrahmanirrahim. Today we are going to discuss the topic synthesis of aromatic compounds. The key concept in this lecture will be electrophilic aromatic substitution. A bit introduction of that will be given. Mechanism. Disconnection in FGI, synthone illustrated by Friedrich's isolation. Then will be discussed the synthones which are suggested by Friedrich's alkylation. Then functional group addition that will be illustrated by Friedrich's alkylation. Then reliable reagents for electrophilic substitution. Now here we are just as a review, I am going to discuss in very briefly what is electrophilic aromatic substitution and how it takes place, a brief mechanism. So because in the retrosynthesis we shall come across the retro of the compound. For that you must know the synthesis and the process. Electrophilic aromatic substitution is an organic reaction in which an atom that is attached to an aromatic system, usually the atom is hydrogen, which is replaced by an electrophile. So what are we saying? That when one mostly hydrogen of an aromatic system is replaced by an electrophile, that is called electrophilic aromatic substitution. Electrophile has substituted one substituent of aromatic ring, mostly hydrogen is that. Some of the most important electrophilic aromatic substitutions are aromatic nitration, aromatic halogenation, aromatic sulfonation, and alkylation, and alkylating Friedrich reactions. The overall reaction mechanism denoted by SEAR begins with the aromatic ring attacking the electrophile. Now you must know that electrophile is any electron-loving species. So the mechanism starts with the attack of electrophile. Usually we say the attack of electrophile, but actually electrophile never attacks, but our aromatic ring attacks on the electrophile. Of course, charge, negative electron density will be attacking on the deficient species. So, as far as mechanism is concerned, the first step, which is the attack of aromatic ring on the electrophile, leads to the formation of a positively charged cyclohexadienyl cation. This cyclohexadienyl cation is also known as arenium ion or arene sigma complex. Normally we call it the sigma complex. The net result is the replacement of hydrogen by electrophile in the aryl ring. Occasionally, other electrofugues are those groups which can leave without their electron pair. Electrofugues which are leaving, fugue means moving away from something. So electrofugues mean those groups which are leaving without their electron pair. Besides H positive will depart to re-establish aromaticity. Now these species include those which we are saying that electrophile. These include silyl groups, SiR3 positive, carboxy group, CO2, H positive, iodo group, iodine positive, and tertiary alkyl groups like tertiary butyl Sr positive. So what are we saying here? We are saying the mechanism takes place by the number one is the attack of aromatic ring on the electrophile. The result is the formation of uranium ion. Now, and after that there will be replacement of hydrogen. Electrophile will be added into the ring, and at the last we have said that other electrofugues beside H positive will depart to re-establish aromaticity. These species include electrofugues, which we are calling other electrofugues, which we are calling like silyl or carboxy or other these electrofugues. These species, these groups with that can live without their electron pair. These species include electrofugues include silyl group, carboxy group, iodo group, and tertiary alkyl groups, tertiary butyl. And hydrogen H positive will live in usually H positive will live in this process. Now here you can see step 1, where electrophile is being attacked by the electron density of the aromatic ring. There is a double-headed, not double-headed arrow, but a double half arrow is being shown, because this reaction is a reversible reaction, and as a result of this reaction uranium ion is produced, which is actually in resonance. So when electrophile is attached on this position where hydrogen is attached, this hydrogen is shown to be attached. When electrophile is attached here, the bond is offered to electrophile to be formed between carbon and electrophile. There will be this carbon which is containing electrophile hydrogen and attached with other two carbons is satisfied, but the carbon, ortho carbon to the position where electrophile is attached, is a deficient carbon. It will carry a positive charge. Now you can see the resonance. First resonance form, the double bond will move from the near double bond will move toward the deficient carbon. It will make a bond, and in turn the next carbon, the para 1 carbon, will become deficient, and the neighbor double bond will come to compensate the deficiency of this positive charge or deficiency of this carbon, para carbon. Then there will be a double bond between para carbon and meta, but in turn ortho carbon will be deficient. So in this way the uranium ion is stabilized. Now how the proton loss takes place in the second step. In the second step, as you can see that there is hydrogen in the last one, canonical form of uranium ion. The hydrogen is the bond between hydrogen and carbon is being donated to the ipso carbon and ortho carbon, and then a double bond is generated over there. In turn the aromaticity is regained and hydrogen is moved away. This is as a H positive ion, and electrophile is attached to the ring. This is all about electrophilic aromatic substitution. Why are we starting with the synthesis of aromatic compounds? First of all, in the retrosynthesis, after discussing the basic concept, because in the aromatic ring the bond which we consider for the disconnection is mostly always means mostly always it is the bond that is joining the aromatic ring to the rest of the molecule. Like aromatic ring, the bond which is directly attached with aromatic ring, that is mostly thought to be disconnected. Only we have to decide two things: when to make the disconnection, when we want to disconnect the bond, and exactly which starting material to use. Like after disconnection, what are the starting materials? After disconnection, synthones will be formed, and after the formation of synthones, we shall have to think what exactly what starting materials we can use for the synthesis. So whenever we're talking about the retrosynthesis, we first have to make the disconnection, logical disconnections. Synthones are the results of logical disconnection, synthones. Then these synthones definitions will come after in afterward slides along with the examples, so that will make the things more clear. So after the formation of the synthones, we have to think about the exactly starting materials that can be used. So what will be the terms which will be mainly used in the chapter are disconnection. Second one is the functional group in interconversion, FGI, and then the synthone. So here we are going to discuss disconnection and FGI. What is disconnection and what is FGI? Disconnections by definition are the reverse of non-reliable reactions. For example, in here the structure number 1 you can see is local anesthetic benzocaine. So it is containing an ester group, and we know that esters can be reliably made from the derivatives of acids and alcohols. So we can show that the disconnection of this carbon to oxygen bond. So in 1a we can see that there is a wiggly line which is showing the disconnection, the bond between the carbonyl carbon and ethoxy oxygen, carbon to oxygen bond is being shown to be broken down. A wiggly line is showing this bond is being disconnected. C2O, the ester bond. So we know that esters are formed from acids and ethanol. So acid, the number in the structure is shown as 2. So the acid, this one acid and ethanol when will react, compound 1A or benzocaine will be formed. And now we will have to see that the compound 2 is further, how can we get that compound 2? How can we proceed further disconnections to get compound 2 from simple raw materials or from simple commercially available chemicals, you can say that. So there are two disconnections possible. Either we can disconnect NH2 or we can disconnect carboxylic acid group. But as if you people think logically, both of these disconnections, either of these disconnections will not give good reactions. Like the reactant which will be having one of these groups and other group detached, they cannot be produced, the compound 2 cannot be produced by any good reaction from those reactants which are obtained by disconnection of one of these two groups. So another strategy we shall use FGI, functional group interconversion. Now what is functional group interconversion? Functional group interconversion does simply mean that you are showing the conversion of one group, functional group, into another one. Like if NH2 attached with the benzene directly is not commercially available, so you can easily get it from nitrobenzene. Like nitrobenzene can be converted into amino by simply reduction. So by definition, if we see what is FGI, then we can say that operation of writing one functional group for another. Like we are replacing one functional group, or we are thinking to create or to transform or interconvert that functional group from some other functional group. So FGI is an imaginary process, just like a disconnection. As we have seen, the disconnections are imaginary. If we want to get a target compound, we just imaginary think about the disconnections to get the starting materials, to think about the starting materials from which that can be made. Similarly, FGI is also an imaginary process. And the reverse of this FGI is a real reaction. Now, as I have told you that amino group can be prepared by the reduction of nitro group. So when we apply FGI, structure 3 will be there. Like we say that that would have been produced, that can be produced amino group from the reduction of nitro. Now, if you look at structure number 3, it is having a carboxylic group along with the nitro group. So carboxylic group, there is not a good disconnection. Like carboxylic group, if it is disconnected from the benzene ring, we cannot directly generate that carboxylic acid group. But there is another very good FGI which we can apply. Like we can convert side chain to carboxylic acid by simply side chain oxidation. So we think FGI again, and what shall we do? That we can as is shown in structure 4. So we thought that it can be produced from para-nitrotoluene, structure number 3. So we went back, we have applied FGI, and structure 4 is obtained. So by the oxidation, 4 is our starting material, so just we can do the oxidation of side chain in 4. Methyl alkyl, any side chain can be oxidized using KMnO4. So we can get compound 3 by simply oxidation of compound 4. So now, if one other option, if we disconnect nitro, now from nitro is not without nitro is more simpler reactant and commercially available reactant is obtained. So we disconnect nitro, we shall be left with toluene, which can be nitrated easily in the para position by mixture of nitric acid and sulfuric acid. If we want these substitute at para position, so sequence will also matter. So which substitution should be done first, and which substitution should be done at the second level. Firstly, what substitution should be done, and secondly, what should be done. So we are going to discuss in the next slide. Now the synthesis of our target molecule will be written. We cannot predict exactly which reagents and conditions will be successfully used. No sensible organic chemist would attempt to do this without studying the related published work. It is enough to make the suggestions for the type of reagent needed, and we shall usually give the reagents used in the published work and conditions and where they seem to matter. So as you can see here, now we are going to do the synthesis. So we have taken toluene, we have taken toluene, and we have done nitration of toluene. Simply we took toluene, compound 5, we have done nitration of toluene, para-nitrotoluene was made, we have done CHEM4121 oxidation, we have done oxidation in the presence of CHEM4121, side chain oxidation took place, and toluene methyl group has been changed to carboxylic. It is group structure 3. Then we have done the reduction of nitro group into amino using palladium over carbon, hydrogenation in the presence of palladium over carbon. Then structure 2. Further we have made the ester of this carboxylic acid group using ethanol, an acidic medium. So our target molecule 1 that was produced in this sequence. Now with this synthesis reaction, we can predict exactly which reagents and conditions will be successful. If we do the retro, we can know very logically that what should be the conditions and reagents used. Here it is important to nitrate first and oxidize second to get the right substitution pattern according to the orientation of the substituents. So this example is done. Now we are going to check another analysis, and the topic is synthones illustrated by Friedrich acylation. In the previous reactions we have seen FGI, and we have seen a disconnection of ester, and then we have utilized 2 FGI functional group interconversion. Now we shall see that how we can apply Friedrich acylation to get the synthones. Synthones are the results of disconnection. After disconnection, what is obtained, we are having a target molecule, and after the disconnection of the different functional group from the target molecule, the material which is obtained with the imaginary disconnection, these are called synthones. Synthones are the materials which we can use to prepare the products, the target material. So now, if we are going to do the Friedrich acylation, as you see in this example here, like 6A, with disconnection of 6A is taking place. So the compound 6, you can see that the compound 6 is actually having one ketonic functionality and one methoxy functionality para to each other. First of all, 6A useful disconnection can be Friedrich acylation of aromatic rings. So the ketone which is present at the para to methoxy, so that will be, so it's Friedrich can be synthesized from the Friedrich acylation of simply compound 7, you can see in the slide. So 7, just logically disconnect by a wiggly line. So wiggly line is used to disconnect the functionality, and we can get both, we can get 2 synthones. One is 7, I'm talking about 6A right now. So one, the disconnection of this functional group in the 6A shown by the wiggly line. C to C disconnection is being done, C of the carbonyl carbon, and second carbon is one of the carbon of the aromatic ring. So C to C disconnection, Friedrich after thinking about the Friedrich acylation, C to C disconnection has been taught. So that gave 2 synthones, 7 and acid halide. Now this synthone, that is CH3 C double bond OCl. This is what? Please have a look at it. This is actually is derivative of acid. When there is a carboxylic acid, C double bond OH, and we replace OH by Cl, we get this. So we shall be discussing it afterwards, but till here I'm just going to read the points so that the things will be clear to you. So this is the first one, the useful disconnection 6A correspond to Friedrich isolation of aromatic rings, is the obvious one on the ketone 6 having the perfume of hawthorn blossom. So here the example of 6 is given, and it's told that Friedrich isolation, thinking about Friedrich isolation, this connection will be take place. Reaction of ether 7 with the 7 synthone with the other reactant acid halide and aluminium chloride will give 6 in 90 to 96% yield. This is an actual reaction. With these two 7 and acid halide react with each other, 6A is produced. Our first choice is disconnecting a bond to benzene ring and to look for a cationic reagent. Right now we are thinking about that there will be a cationic reagent which shall be used, so that we can use electrophilic aromatic substitution. As all of you know that in electrophilic aromatic substitution, electrophile comes and it acts on the benzene ring, and benzene offers one of its three bonds to make a bond with new incoming electrophile. Uranium ion is formed, and then afterwards the uranium ion is stabilized by removing another hydrogen from the benzene ring. So in that case, electrophilic aromatic in the case of electrophilic aromatic substitution, keeping in mind electrophilic aromatic substitution, now we shall think the last point. If we check, we know not only which bond to break, but also in which sense electronically to break it. Now this point is left to discuss that, to explain that we look point number 3 in this paragraph. Our first choice on disconnecting the bond to a benzene ring is to look for a cationic reagent. So we are going to discuss in the next slide also for how cationic reagent. So now if we logically disconnect 6A, there can be two types of synthones. In one type of synthone, in disconnection A, from 6A 10 and 11 have been produced, and in the other one, disconnection B, from 6A, two synthones 8 and 9 can be imagined. Word imagined or suggested would be better rather than produced. So what are actually synthones? Synthones are idealized ions that may or may not involve in the actual reaction, but they actually help us to work out which reagent to choose for the synthesis. Now if we discuss, the synthone 11 is a real intermediate, while the other are not the real intermediate. In both these reactions, the above one where we were nitrating the toluene for making benzocaine, and now in this reaction when we are going to do the Friedrich acylation, the reagents are actually cations. Previously the reagent was nitronium ion, that was also a cation for nitration. Now for Friedrich reactions, the reagent is again a cation, and that is 11 cation. Our first choice on disconnecting a bond to a benzene ring is to look for a cationic reagent, because in the electrophilic aromatic substituents, an electrophile will come towards the benzene. An electrophile itself is an electron deficient species most of the times. So we know not only which bond to break, but also in which sense electronically to break it. So when we are talking about disconnection A, quite logical synthons have been formed. So we in principle we could have chosen either polarity from the same disconnection A and B, but we actually choose A. The reason was that there was a logical disconnection. The synthons which we are suggesting are actually logical. The synthons which we are suggesting are existing even, but in the case of disconnection B, positive charge on the aromatic ring at the carbon, which is being disconnected from the carbonyl, and the carbonyl carbon with the negative charge are not real synthons actually. So how can we make that synthon 11? Synthon 11 can be suggested from the acid halide, and if the halogen of the acid is removed, acid halide is formed. So synthon is a real intermediate, only the 11-1 synthon, others are not. Now for the anionic synthon like 10, the reagent is often the corresponding hydrocarbon when H positive is lost from here during the reaction in 10. How 10 is formed? By the loss of H positive ion from the aromatic ring. 10 can be produced like this. As there will be more experience in the retrosynthetic analysis, this we shall be an increased sense of drawing the synthons, and we will come to know that what are the logical disconnections. Now the synthons which are illustrated by Friedrich alkylations. So keep in mind this rule that for doing disconnection, first you should be knowing reliable chemical reaction by which that the target molecule can be prepared. The synthons which are formed by the disconnection must be logical. So here we can say that the target molecule BHT number 13, butylated hydroxytoluene. If we want to disconnect, we can do the disconnection either we can remove methyl group or a bond to remove tertiary butyl groups, or we can disconnect the bond to remove both, like both tertiary butyl groups. Like A disconnection, if you look into the structure 13, there is a disconnection labeled as A in which tertiary butyl groups are being removed. So in the case of disconnection A, both can be removed, like we think of disconnecting the both, or in case of B, we shall disconnect bond of methyl. Now we can see by doing these disconnection, the result of the disconnection, C to C bond disconnection, we got synthone 14 and a methyl cationic radical. So by the disconnection of carbon to carbon bond of tertiary butyl, we got two synthones, number 15 and the other one, number 15, and the other one is tertiary butyl cation. Number 15, paracresol, that is an available chemical, whereas the 14 is not an available chemical. So in tertiary butyl cation, if you look, is very much stable than the methyl cation. So finally, one more important thing is that hydroxyl group is more powerfully orthoparadirecting than the methyl. We have, if we see the sequence of strength of orthoparadirecting activating groups, so hydroxyl is more stronger activating orthoparadirecting group as compared to methyl. So although OH will be directing the here, if we choose OH after the reaction, OH the substitution will be taking place at ortho position to OH, because it is more powerful activating orthoparadirecting group, and there is a rule that if two groups compete with each other in the direction, in the orientation, the group which is having stronger activating or group will be determining the position of the incoming electrophile. So here you can note that 15 doing the reaction with the substrate in the presence of acidic conditions, we got 13 BHT. So there is double bond, there is alkene which we have choice to react with 15 to produce this. So that for the choice of reagents for tertiary butyl cation, we can choose a halide with Lewis acid catalysis and a tertiary butanol or isobutene with protic acid. So look at the synthones again. When we are going to choose the reagents, we should have to think about what substrate can give us tertiary butyl cation, required tertiary butyl cation. So tertiary butanol if we use, or isobutene if we use in acidic conditions, that can provide tertiary butyl cation to the 15. So the least wasteful is the alkene, as nothing is lost. When we use alkene, we just directly give the product 13. In the case of acidic conditions, that alkene is just added to our substrate 15. So protonation gives the tertiary butyl cation, and two tertiary butyl groups are added in one operation. Now if we look at target molecule 16, right, so for preparing isobutyl benzene 16, we should first alkylate the benzene with isobutyl halide. For example, 18, we can first we can just alkylate the benzene with isobutyl halide to for example 18 here in the picture is isobutyl halide. So alkyl halide and aluminium chloride. In the presence of aluminium chloride, alkyl halide can do the electrophilic substitution on benzene. This is electrophilic substitution, or you can say the Friedrich alkylation. Now the question is that when we disconnect 16, we got 17 structure. A cation is needed, and we can, from where this is a synthone 17, but the synthone can be provided. There should be a real molecule that can provide our synthone. So 18 is the molecule we thought that can provide 17. So from where that 18 came. Now the reaction 2 gives the products 21 and 22. So what is reaction 2? Reaction 2 is actually when alkyl halide in the presence of aluminium chloride is being activated to give 20. Cation will be generated by the reaction of alkyl halide with aluminium chloride. You can see 18 in the presence of aluminium chloride is giving 19, which in turn is producing 20 cation. That is a isobutyl group. So both contain instead the tertiary butyl group, 21 and 22, both. So instead of that substitute which we needed, that is not producing the required compound, but it is adding tertiary butyl group to our substrate benzene. One synthone you can see in the first disconnection there was 17. The disconnection of 16 gave us 17 and one benzene. So when we tried to add 18 with benzene, Friedrich alkylation, we got two products, 21 and 22, but both were having tertiary butyl group rather than isobutyl group. Now the intermediate complex rearranges by hydride shift 19 into the tertiary butyl cation 20. So there are hydride shifts taking place, and the primary cation, which is actually formed after the removal of chloro, that is interconverts, or that is rearranged by hydride shift into 20 tertiary butyl cation. It converts it by hydride transfer into tertiary butyl compound. So 17 is too unstable, because you know that as comparing the stability of cations, primary cation is less stable. Primary cation here 17 is less stable than 20. So the rearrangement takes place, which converts less stable cations into more stable cations. Now if we check that compound number 23, if we use rather than compound 18. Compound 18 is an alkyl halide, while the compound 23 is acyl halide. So when this acyl halide is added in the presence of aluminium chloride, we got 24, and then I can that you have acylated benzene rather than alkylated. After getting that acylated product 24, we reduce the acylated product, and in the presence of zinc mercury amalgam, concentrated HCl was present. We got the target molecule 16. Now so we can disconnect it rather than the above disconnection which we have done in the first reaction. We can disconnect. First we do the FGA, functional group into conversion. We have converted simple 16 molecule into the 24. Like we can say that we have interconverted the functional group. We have converted a simple alkane into the ketonic functionality, and then we have done the disconnection to give syntones 23 and benzene. Now, polyalkylation was an advantage in the synthesis of BHD 13. It is the rearrangement that is chiefly unacceptable here, because the rearrangement, polyalkylation is a disadvantage of this reaction basically. So Friedrich acylation avoids this problem. I use the word advantage, but it is actually there should be actually disadvantage. It is disadvantage. So polyalkylation is a disadvantage in the Friedrich alkylation. So acyl group does not rearrange and produce is deactivated toward further electrophilic attach by the electron withdrawing carbonyl group. So the carbonyl group stops is for further any electrophilic attach. So it deactivates the group. So we have an extra step, reduction of ketone to CH2. We had to do the reduction of that 24 ketonic functionality into CH2, but we did not get a rearranged product 21 or 22 in the case of acylation. Now, as far as the reliable reagents for electrophilic substitutions are considered, here is a table in which the reagents for electrophilic substitution are tabulated. If you review or remind the electrophilic substitution reaction, there are 3 steps in that. In the first step, electrophile attacks on the aromatic ring, but actually the aromatic electronic density attacks on the electrophile. Well, whatever, if some things are traditionally written like electrophile attacks, but actually the aromatic electronic density attacks on the electrophile. After the attachment of the electrophile, uranium ion is formed, and then the delocalization takes place, that uranium ion, and that is stabilized. And in the third step, the leaving group leaves, and the aromaticity is regained. So, keeping in mind the main electrophilic substitution reactions, here are these tabulated, and syntones and the reagents for them are also tabulated. For example, Friedrich alkylation, whenever you will see any R group, any disconnection of the aromatic ring, disconnection of R plus group, means syntone will be R plus, then the reagent, possible reagent for that can be alkyl halide in the presence of aluminium chloride. Friedrich alkylation. If you see an acyl syntone, then you can think of the Friedrich acylation, and the reagent would be acid halide. Then if you are disconnecting nitro plus group from aromatic ring, then the possible reagent for that should be the nitrating agent. So nitration will be the process for that, reaction for that. When you see chloro plus, bromo plus ion, cation, or when you